welcome to the deep dive. Today, we're going on a bit of a journey, actually, into the unseen.
Yeah, the stuff that powers pretty much everything now. Wi-Fi, GPS, all those invisible connections.
Exactly. And we're zoning in on one person, Heinrich Hertz. He's the guy who, well, he didn't invent radio, did he?
No, not really. But he did something arguably much bigger. He showed that James Clerk Maxwell's equations, these complex mathematical ideas about electromagnetism, weren't just math.
They were real motion happening out in the world.
Precisely. So today, we've got a stack of material, research papers, historical accounts.
And our mission is to pull out the key insights for you. We want to unpack how Hertz made the invisible visible.
And we'll explore how a different way of thinking, called motion theory, gives us a really fresh, kind of intuitive grasp on what he actually achieved.
So get ready for some aha moments, because we're talking about what it really means for, well, motion to leave the wire.
What Hertz fundamentally showed, you see, is that the world is full of these. Let's call them self-propagating synchronization patterns.
Okay, break that down a bit, like ripples.
Sort of, yeah. Imagine a structured motion, a rhythm, that can actually detach itself from, say, a piece of metal wire.
And just travel through space.
Right. And it can cause something else far away to start moving to the exact same beat. He basically turned abstract math into a measurable rhythm.
Wow. And he did this in his lab in Karlsruhe, right? A pretty quiet place, I imagine.
Uh-huh. And in that quiet lab, he summoned waves. Invisible waves, sure, but they acted just like light.
How so?
Well, they reflected off things, they bent when they went through different materials as refraction. They could be polarized. They even interfered with each other.
But they weren't light, we could see.
No, these were big waves, meter-long wavelengths, so he could actually, interact with them using fairly simple kit like wire loops and metal sheets. He was feeling out the invisible.
Let's get into that iconic experiment then. The spark, the loop, and the leap. How did he set it up?
Okay, so the core was his exciter. Think of it as the source. It used a Ruhmkorff coil, basically a high-voltage generator.
Right, makes sparks.
Yeah, driving a tiny spark across a gap between two polished metal balls. Now, this setup wasn't just random sparking. It formed what we call a resonant LC circuit.
Like an electrical tuning fork.
Good analogy. It had a natural frequency. And each spark was like a sharp, violent hit on that circuit, causing a burst of really high-frequency oscillation, a sudden pulse of rhythm.
Okay, so that's the transmitter, the shout.
Exactly. And if you look at it through this motion theory lens, it's like a little loop of energy that's been kicked hard, knocked out of its equilibrium.
And the spark itself.
That's the stored energy collapsing, bursting out as this tight, short-lived rhythm. Now, the brilliant part, across the room, he put his resonator.
Which was?
There's a simple loop of wire with its own tiny spark gap, nothing connected to the first one. And when the exciter sparked, this distant loop, it flashed. A tiny spark jumped across its gap, in sympathy, as Hertz put it.
Whoa, in sympathy, that's amazing. So it wasn't just like a magnet getting weaker with distance.
No, definitely not. Simple induction falls off way too fast. Hertz was super careful, methodical. He changed the distance. He rotated the loops relative to each other, altered their shapes.
And what happened?
The resonator only sparked properly when it was positioned and oriented just right according to a specific wavelength and direction. It wasn't just about being close.
Ah, so that was the proof.
That was the smoking gun. The motion, the rhythm, had left the wire and crossed the room.
And motion theory sees that resonator as
a listening loop, tuned perfectly to the rhythm being sent out. And the space in between. It's not empty. It's the medium that carried the phase transmission.
like the ripple moving across the pond.
Exactly. Allowing that distant resonator to entrain, to lock onto and replicate the rhythm, it changes how you think about what's actually moving. It's not necessarily stuff. It's a pattern.
Okay, so he proved it travels, but he went further, right? He showed these waves were like light waves, reflection, refraction.
Yep. He bounced them off big sheets of zinc. Found they obeyed the law of reflection angle in equals angle out, just like a mirror does with light.
And refraction, bending through materials.
And made prisms, not out of glass, but out of pitch, like tar and sulfur. Passes waves through them, and sure enough, they bent according to Snell's law, the same rule light follows.
So from a motion theory view, what's happening there?
Reflection is like a phase reversal at a boundary. The rhythm hits the wall and flicks its step, so to speak. Refraction is a phase velocity change. The rhythm slows down or speeds up as it enters the new material, changing its direction.
Makes sense. What about polarization? That's a key property of light.
He demonstrated that too. He built these grids of parallel wires. If he held the grid one way, the signal got through to his resonator.
Okay.
But if he rotates the grid 90 degrees, poof, signal gone. Rotate it back, signal returns.
Meaning the wave vibrated in a specific direction, perpendicular to travel.
Exactly. Transverse waves, just like light. Motion theory calls this the directional coherence of the moving rhythm. The pattern has a specific orientation.
And then the really clever bit, I think, mapping the waves in space. Standing waves.
Oh yeah, that was ingenious.
Yeah.
He put a big reflecting sheet up, creating interference between the outgoing waves and the reflected waves.
Like ripples meeting each other.
Right. And where they met in step, the signal was strong, an antinode. Where they met out of step, they canceled out a node. A quiet spot.
And he found these spots.
He moved his little resonator loop around in front of the reflector and literally mapped out these zones of strong signal and no signal. Bright and dark zones, you could say.
And the distance between the quiet spot.
That gave him a direct measurement of the wavelength. How cool is that? He's measuring the invisible structure.
So incredibly clever. Motion theory sees this as
Pure phase addition and subtraction. Rhythms reinforcing or canceling. And the standing wave pattern itself is rhythm trapped by geometry.
Okay, so he has the wavelength from the standing waves, and he could calculate the frequency from his exciter circuit.
Right, from the size of the components, the inductance and capacitance.
So wavelength times frequency.
Gave him the speed. And guess what it was?
The speed of light.
Bingo. See to it. It was the ultimate confirmation of Maxwell's theory. He'd closed the loop experimentally.
And almost as a side note, that simple wire antenna he used, the straight wire with the spark gap in the middle.
The Hertzian dipole, yep, that's the granddaddy of basically every antenna we use today.
Right.
Your phone, your Wi-Fi, router, they all owe a debt to that simple setup.
Amazing. And motion theory's take on c, the speed of light.
It sees c not just as a speed limit for stuff, but as the maximum rate at which the underlying substrate can carry synchronization. The ultimate tempo for phase patterns propagating through space.
Now, you mentioned he observed something else too, almost by accident, something about ultraviolet light.
Yeah, a little detour, but fascinating. Back in 1887, he noticed that if UV light shone on the metal spheres of his detector spark gap, the spark jumped more easily.
Easier. Why? Did he figure it out?
He noted it down, published it, but didn't really chase it. He was focused on the waves. But that observation, that was the first hint of the photoelectric effect.
Which Einstein later explained with photons, right?
Exactly. It was the seed. But from the motion theory angle, it's interesting too. It's just the UV light, that external rhythm, was altering the local phase landscape right at the metal surface.
Making it easier for the spark.
Yeah, kind of priming the carriers, lowering the energy barrier needed for the electrons to jump the gap and complete the circuit. It lowered the phase lock threshold, you might say.
Okay, this brings up a really important point. Maxwell's equations work incredibly well. They predict all this behavior. So why bring motion theory into it? Why do we need another way to look at it?
That's a fair question. And the answer isn't about replacing Maxwell. His equations are solid gold. They tell you how things behave with incredible precision. But they don't necessarily dictate the ontology, the what it isness of it all, what's really going on underneath the math. Motion theory keeps all the math, all the predictions, Lorentz invariance, everything.
But it offers a different interpretation, a different picture of the reality.
Exactly. It offers a language focused on dynamics, on rhythm, on synchronization, which can be, for many people, more intuitive.
So let's try that comparison. Hertz's spark exciting the distant loop. Standard view.
Standard view. Electromagnetic waves radiate outwards.
Motion theory view.
A phase burst entrains a remote loop via the substrate. It emphasizes the pattern transfer.
Okay. Reflection and refraction. Standard view relies on
Boundary conditions in the math. How the fields behave at an interface.
motion theory.
Phase geometry changes at interfaces. The pattern itself interacts with the boundary.
Polarization. Standard is the orientation of the electric field, right?
Transverse E-field orientation, yes. Motion theory describes it as the directional coherence of the moving rhythm. The pattern has a clear directionality.
Interference and standing waves. Superposition in the standard model.
Right. Waves adding up. Motion theory calls it phase addition, and standing waves are trapped, rhythm-forming nodes.
They're the speed of light.
Standard,
Yeah.
EM wave speed, motion theory, max sync rate of the substrate.
Even the photoelectric effect. Standard. Photon knocks out an electron.
Motion theory. Incident rhythm lowers the phase lock threshold at the surface, makes it easier for the electron to get loose.
It's quite a different flavor, isn't it? Hertz was all about measurement, making it real. Motion theory seems to really lean into that dynamic, patterned reality.
Yeah, it shifts the focus from things moving through space
Hmm.
to patterns propagating in space, turning other loops into copies of themselves. Is a very active, interconnected picture.
And this connects to near field and far field, concepts we hear a lot in wireless tech. Hertz's lab was kind of on the edge of these.
Right on the border, yeah. These are really two regimes of how that energy behaves after leaving the source.
So near field first, what's that about?
That's the zone really close to the source. Think within a wavelength or so. Here, a lot of energy is reactive. It sort of sloshes back and forth, building up and collapsing the electric and magnetic fields right around the antenna.
Doesn't really radiate away efficiently.
Not as radiation, no. The coupling drops off really fast with distance, like 1 over r cubed or even faster. You're essentially still part of the source's immediate environment, almost sharing a loop.
Motion theory calls this.
Loop entanglement,
Okay.
like gears meshing closely. This is
Huh.
how things like wireless charging pads or induction cooktops work. Close coupling.
Okay, and the far field.
That's further out, beyond a few wavelengths. Here, the energy is properly detached.
Yeah.
The electric and magnetic fields are in sync, marching together, carrying energy outwards.
And the signal drops off slower.
Much slower, just 1 over r. The wave is self-propagating now, carrying its own phase scaffolding. Motion theory calls this self-carrying rhythm.
And that's radio, Wi-Fi, GPS signals meant to travel.
Exactly. That's the realm where Hertz proved motion truly leaves the wire and travels independently.
Which makes his famous quote even more striking, doesn't it? I do not think that the wireless waves I have discovered will have any practical application.
Yeah, the irony is thick there, isn't it?
Yeah.
But, in a way, it shows the proper scientific mindset.
How so?
His job, as he saw it, was to prove the phenomenon existed, to measure it, to understand its behavior according to the laws of physics. That's the core science.
And leave the engineering and applications to others.
Pretty much. Prove it first, map it out, then maybe think about uses. It aligns perfectly with that motion theory idea. Measure first, myth later. Nail down the reality before you build stories or technologies around it.
His whole method feels like a blueprint for discovery. Motion theory kind of formalizes it, right, into steps.
It does. You can break down the Hertzian method. First, build a clean loop. That's your exciter, your source. Make sure it has a controllable, predictable rhythm or beat.
Step 2.
Design a listener, your resonator. It needs to be selective, tuned only to the rhythm you're sending.
Then you have to show it's really traveling.
Step 3. Prove detachment. Show the signal isn't just proximity effect. Distance and orientation matter in a wave-like way. The rhythm leaves the source.
Step 4 is checking its properties.
Probe geometry. Use reflection, refraction interference to see how the phase pattern behaves. Expose its rules.
And finally, nail down the constants.
Step 5. Extract invariance. Like measuring wavelength and frequency to confirm the speed is C. And crucially, throughout all this,
Try to break it.
Step 6, invite falsification. Rotate things, yield things, detune things, block the path. Does it behave as predicted? That's how you build confidence.
So motion theory boils that down to
A make, match, separate shape, measure. It's the fundamental lab cycle for exploring these kinds of phenomena.
And you can really see Hertz's influence still echoing today, can't you? In antennas, for instance.
Oh, absolutely. We've gone from his simple dipole to complex phased arrays, MIMO systems.
Yeah.
But fundamentally, beamforming, steering a Wi-Fi signal right to your laptop that's just programmable phase.
Yeah.
We're actively sculpting that rhythm Hertz first detected.
What about metamaterials? They seem almost magical.
They're amazing. Tiny engineered structures that manipulate waves in weird ways, artificial refraction, invisibility cloaks. What they're really doing is sculpting the phase response of the material itself at a subwavelength level. Pure Hertzian thinking, just with modern tech.
Terahertz science too, right? That's kind of Hertz's original frequency range.
It is. We're revisiting that part of the spectrum, but now with incredibly precise, ultrafast tools. It allows imaging by rhythm, seeing through things that visible light can't penetrate.
And even faster stuff, photonics.
Ultrafast photonics uses femtosecond laser pulses, unbelievably short bursts of light. You can think of them as designer bursts of phase. Scientists use them to probe how materials react, how quickly they rephase after being hit. It's mapping dynamics on the fastest timescales, all building on Hertz.
Okay, let's tackle a few potential points of confusion head on. We touched on it, but again, why motion theory if Maxwell works?
Right. To be crystal clear, motion theory doesn't contradict Maxwell. It accepts the equations fully. It's an ontological interpretation. Maxwell describes the how. Motion theory offers a way to visualize the what-seeing waves as traveling synchronization, propagating patterns rather than mysterious field lines in a void. It's a conceptual overlay.
Got it. Second confusion. Does this bring back the ether, that old idea of a physical medium filling space?
Definitely not. There's no fixed background, no preferred frame of reference, no ether wind to detect. The substrate in motion theory isn't a substance. It's more like a set of rules, a relational field that ensures phase relationships are consistent across space, and that the maximum speed for propagating these phase patterns is c. It's about the structure of space-time relationships, not a physical jelly.
Okay, clear. And the big one. Where do particles like photons fit into this picture of continuous rhythms and patterns?
That's maybe the most interesting part. Quanta, particles. They emerge when the system is forced into a discrete state, when constraints force discrete rephase events.
Like when light hits a detector, or an atom emits light.
Exactly. Those are interactions, constraints. That's when the continuous wave-like rhythm manifests as a particle-like event, a specific energy packet exchange. But between those interaction points, the rhythm, the phase evolution, is continuous. It offers a way to perhaps reconcile wave-particle duality. It's always a phase pattern, but it appears particle-like upon interaction.
So, wrapping this up, Hertz's legacy is just immense.
Monumental. He took Maxwell's beautiful abstract theory and literally connected it to the physical world. He closed that loop.
And in doing that, he opened up everything wireless we use today. Radio, radar, Wi-Fi, remote controls, GPS, even things like medical imaging and ultrafast science.
He proved that space itself isn't passive. It can carry a tune, and that we, through our circuits, could teach space our rhythms.
His method endures too, doesn't it?
Absolutely. Build a rhythm, release it, and then walk around in it with a detector until the invisible becomes a map. That's the essence of how science learns to perceive these hidden realities.
That's how science learns to hear. And once you can hear, you can orchestrate. It was always motion. Hertz just proved it travels.